Welcome, fact lecture. Now, in the previous lecture, we were discussing about thyristor switch series capacitor. So this is the basic diagram of thyristor switch capacitor. And already we have discussed the operation of thyristor switch capacitor and their waveform. From this waveform, that is the voltage across capacitor, our objective is to control the voltage across capacitor. So now the voltage across capacitor is this one. This is the when the one of the thyristor, say thyristor T2 is in conduction mode. So when thyristor T2 is under conduction mode, the current is going to flow from the thyristor and voltage across capacitor is equal to 0. So this is voltage across capacitor is 0. Now the total switch means thyristor T1 and T2 both are non-conducting mode, that is a off mode. Switch is off. So this is the voltage across capacitor, and so it will give the voltage across capacitor for different switching of the thyristor T1 and T2 and making off. So it is quite clear the frequency of voltage across capacitor is quite different as compared to the frequency of current of the transmission line. Okay, so see here, this is one complete cycle. This is the one complete cycle of current. This is the transmission line current cycle. And whereas the capacitor voltage will start from here, and it is a positive half cycle, and this is negative half cycle. So this thyristor switch series compensator is slower as compared to the other series compensation. And the second difficulty which is associated with the thyristor switch capacitor, when high degree of compensation K, which is equal to XC upon X or XL, that is the total reactance of the transmission line. If you want a higher degree of compensation, it has become difficult to obtain a high degree of compensation with the help of thyristor switch capacitor. And the second is that, and because of sub-resonance frequency, and it also produced the sub-resonance, subsynchronous frequency or operation. And because of this subsynchronous phenomena, because of the thyristor switch capacitor, it may fracture the shaft of the generator, or it may be the failure of entire generator is there. So this is the difficulty which is associated with the thyristor switch series compensator. So this point was left to discuss about the thyristor switch capacitor. Now today we will proceed our topic, and the today's topic is thyristor control series capacitor. Thyristor controlled series capacitor. Now it may be a thyristor control series compensation. How it is a compensation, but say we will give the name thyristor control series capacitor. So it is thyristor control, so TCSC. So the short name is TCSC, and the basic diagram or circuit diagram for thyristor control series capacitor is the combination of capacitor which is connected in series with the transmission line. So this is the capacitor which is connected in series with the transmission line. So this is transmission line current I, and this is C, and we want to control the voltage across capacitor VC. This is our objective, is to control voltage across capacitor. Now, to make it controllable as compared to the thyristor switch series capacitor, and thyristor switch capacitor, the capacitor is shunted by a thyristor switch, or parallel connected thyristor walls are there. But now we are going to shunt it with the help of a thyristor controlled reactor. So this is reactor. And now this thyristor, this reactor is going to control with the help of thyristors. So this is thyristor 1 and thyristor 2. Let this is thyristor 1 and this is thyristor 2, and it is shunted to the capacitor whose voltage across capacitor is VC, and our main objective is to control voltage across capacitor. So this is the capacitor current, and this current is the current through the reactor, which is the function of inductor current, which is the function of thyristor control delay angle, delay control angle alpha is there. So this is the inductor L, and here this is the basic diagram. Okay, this is also the thyristor. Okay, so this is the diagram which is called as a thyristor control. So we are going to obtain the smooth voltage variation as similar to the JTO thyristor control series capacitor. Now instead of JTO, we are using this part is the thyristor control reactor. This is thyristor control reactor. Okay, this part is that one. Now, what is the value of capacitance or capacitive reactance? So the capacitive reactance XC, which is equal to 1 upon omega C. So this is the fixed value because we are not going to change the value of capacitor. Whereas the inductor value, that is the inductive reactance, XC, XL, which is the function of delay angle alpha. So this is the conduction delay angle. Okay, if you just refer to our previous diagram, which is used, and the equation which we have used for the controlling of the thyristor control reactor, we will see it is the function. The inductor is the function of inductive reactance is the function of control delay angle, isn't it? Now, the total reactance of this TCSC. So we can write the reactance of TCSC, what it would be equal to, which is the combination, which is with the combination of, this is a parallel combination. So XL, XC is the fixed value, whereas XL is the function of delay angle, conduction delay angle, divided by XL, which is a function of delay angle, conduction delay angle, minus X. This is the total effective reactance of series thyristor control series capacitor. Now, as this part of inductor is the function of delay angle, so we can write the total value also depend upon the conduction delay angle or turn on delay angle. So alpha is turn on delay angle in thyristor control reactor. Okay, so this is the one. Now, as we know that the thyristor control reactance susceptance which is indicated by BL, is a function of turn on delay angle alpha. It is equal to, it is already defined, so 1 upon omega L into bracket 1 upon pi minus twice alpha upon pi minus 1 upon pi into sine of twice angle, sine of twice alpha. This is the susceptance. Whereas reactance of TCR, okay, because the TCSC is consist of fixed capacitor in parallel with the TCR. So therefore, TCR reactance TCR reactance XL, which is the reciprocal of susceptance, which is the reciprocal. So 1 upon BL with the function of turn of delay angle. It is equal to, if you put this value in this one, so we get omega L into bracket pi minus twice alpha minus sine twice alpha divided by pi. So this is the value of Thyristor controlled reactor, which is the function of turn on delay angle. Whereas the total capacitive reactance, this capacitive reactance is the combination, parallel combination of the capacitive reactance as well as the inductive reactance. So whereas the capacitive reactance is fixed, therefore we can say that the capacitive reactance is fixed, whose value is equal to 1 upon omega c, whereas the reactance value, value of reactance XL is the function of turn on delay angle alpha. So this is the things, this is very important to understand. Now, what would be the value of say inductive reactance, and what would be the value of capacitive reactance? At alpha is equal to 0 to 90, there is a change in inductive reactance, whereas the capacitive reactance will remain constant. Okay, so at simply alpha is equal to 0, it means that turn on delay angle is equal to 0, and it will conduct, full conduct. So what would be the value? The value of XL is minimum. Therefore, XL is equal to omega L, whatever the value of L, and this is the this one. So just will write by red color. So this is the one condition. When alpha is equal to 0, there is a full angle conduction. Conduction is full, and we get XL is equal to omega L. Okay. So it means T1 and T2 in the positive and negative half cycle fully conducted. It means that. Whereas when alpha is equal to 90, it means the turn-on delay angle is equal to 90, and it acts as a open circuit. So here it is a closed. It is a closed switch. It means that switch is closed. Whereas when alpha is equal to 90, turn on delay is equal to 90 and there is no conduction at all. Therefore, omega XL, which is a function of L at this value, goes to the infinite value. Infinite value means it is an open circuit. It is an open circuit. Why it is open circuit? Because your T1 and T2 is turn off. Turn off. It means that switch is open. It is a open switch. Open switch. So under such condition, the XL is equal to the value is infinite. So it means that the TCSC capacitive reactance varies from minimum. It means that TCSC capacitive reactance varies from minimum value. What is the minimum value? When XC is equal to 1 upon omega C to higher value, and degree of compensation can be controlled. So by controlling the Thyristor control reactor, it is possible to control the entire value of TCSC reactance. That is this one. We want to control the TCSC reactance. Therefore, the TCSC reactance is the function of inductor, isn't it? Now, what would be the value of TCSC reactance at different conduction angle alpha? Our objective is to know, we want to know reactance of TCSC, which is a function of angle, turn on delay angle, is equal to how much at different value of angle, say right from angle which is angle delta alpha is 0, greater than equal to and less than equal to 90. This is our object. We want to know the value of TCSC reactance, total TCSC reactance or compensation value when alpha is equal to 90 degree, when alpha is equal to in between 0 degree or 0 degree, isn't it? So for that purpose, first of all, we have to understand the basic concept. When capacitive reactance become equal to the inductive reactance, it is under the parallel circuit. It is called as a parallel resonance. And under parallel resonance, the total reactance of parallel circuit goes to the infinite value. Isn't it? So under such condition, we do not want and it is prohibited angle at which the resonance is going to occur, and we have to avoid the resonance condition in the TCSC. Definitely there is some TCSC. So to avoid this resonance condition, there may be a limit. There may be a limit of angle alpha. What is the angle alpha? The angle alpha is nothing but the turn on delay angle of TCR, Thyristor controlled reactor. That is a part of a circuit. It is a part of circuit. Limit of angle is the where resonance is going to occur, isn't it? So for that purpose, we say that for the inductive circuit, for capacitive circuit, okay, say for the capacitive reactance, there is a limit of angle from 90 to this angle. So the limit is, say, alpha C limit is the capacitive limit angle to the pi by 2 or 90 degree, isn't it? Pi by 2 or it is a 90 degree. And why it is 90 degree? Because when the angle is equal to 90 degree, inductive reactance become infinite, that is an open circuit. And in the circuit, there is only the capacitive reactance. Just we'll draw one more time the reactance, so it become very easy to understand. This is the capacitor, whose voltage across capacitor we want to control. This is our main objective. This is the current I, is the transmission line current I, and here it is shunted by the inductor, and inductor is going to control with the help of thyristor, anti-parallel connected thyristor valves. T1, T2, and this is shunted. Okay, our objective is to find the total reactance, this parallel combination reactance, which is the parallel combination. So it is a reactance X TCSC, which is a function of turn-on delay angle, is equal to XC into XL. Okay, we'll write. So reactance XTCSC, which is a function of angle alpha, is XC. XL is a function of angle alpha divided by XL is a function of angle alpha minus X. This is the parallel combination. Okay, this is inductor L and this is the current I L. So when angle 90, when alpha is equal to 90 degree, XL is equal to infinite, isn't it? That is an open circuit. Open circuit, isn't it? When alpha is equal to 90 degree, this is, say, it is not present, and the value of capacitance XC is equal to minimum value, and that is equal to XC is equal to 1 upon omega C. That will be the total TCSC reactance, isn't it? So we want to know what would be the limit and what would be the behavior by changing the angle 90 to some limited value. This is the limited value over this one. So we will draw one characteristic. Say this is the axis of angle alpha. This angle alpha is equal to 0. Okay, and somewhere it is a resonance condition. So we will write here, it is this angle is equal to pi by 2, or it is a 90 degree. So alpha is equal to 90 degree. And here somewhere there is a probability where the resonance is going to occur. So this angle, this value is alpha C limit, this one. Now, when alpha is equal to 0, inductive reactance become infinite and the value of capacitance Xc is minimum. So this is the minimum value, say. And as the angle increases, means decreases, the turnaround delay angle decreases less than 90 degree, it is start conducting, and the value of capacitance or the value of total capacitive reactance, TCSC reactance, is gone decreasing. So here it is gone decreasing, sorry, increasing. And somewhere at some that angle, if we go beyond this one, the angle, beyond this angle, the reactance become infinite. So above this one, the reactance become infinite. So this region is the capacitive region. So the limit up to this one is the capacitive one. So this is capacitive operation. Capacitive operation. It means that the reactance of TCSC is capacitive under such condition, and whose limit C alpha C limit is greater than equal to angle alpha less than equal to 90 degree or pi by 2. This is the region, isn't it? Now similarly, this value, it is the angle limit where the TCSC reactance become infinite. And why it is infinite? Because of the parallel resonance condition. So say this angle similar to this one, it is a alpha L limit to the angle alpha is equal to 0 degree. So under such condition, the region, this is the minimum value of inductance, inductive reactance, and now the inductive reactance is increasing, and as soon as it's enter the value of angle alpha over this one, it become infinite. So this is the region is a inductive reactance or inductive value of the TCSC. So this is by which we can say that the total reactance X TCSC is the function of angle alpha. So this region, this in this side, it is a inductive. And in this side, it is a capacitive. Okay. So what is the region for the inductive? Where the angle alpha is equal to 0, greater than 0, equal to and greater than 0, but it is smaller than alpha L limit. So this is the operation of TCSC, and TCSC can be is a capacitive compensation, series capacitive compensation, as well as series inductive compensation. So if the angle alpha is equal to 0 up to the limited angle, it may operate as a thyristor control series inductive compensation. Whereas the angle alpha is greater than and less than equal to 90 degree, it is operating as a thyristor control series capacitive compensation. So instead of calling as a thyristor control series capacitor, one may call as a thyristor controlled series compensation. So in the both side, it is going to give the compensation on the capacitive as well as the inductive. So this is the same. Now, what is that region? This is the prohibited angle. That's why I write over this one. So this angle is the prohibited angle. It should not be operate in this region. Otherwise, there is a parallel resonance. So it is a prohibited region of angle alpha. If as soon as the angle alpha, and it may be say 35 to 45 or 50, whatever it may be as per the values of inductor and capacitor, but this may be the region, and under such region it is going to operate under the resonance condition, and the reactance will be infinite. So it will show the infinite value. So this is the end of thyristor control series compensation or series capacitor. In the next lecture, we will see the switching converter type or voltage source converter type series compensation instead of inductive reactance and capacitance. This one. Thank you.